So hi everyone, I will gonna try in this video to run or to develop a Seep W model for one of the physical model we had in the lab. I will gonna try to show you how to develop this model. There was lots of issues and problems because of the dimensions problem. So the dimensions of the physical model was in centimeter while the Seep W units were in meters, and it was kind of difficult to sketch the physical model. So today I will going to try to show you how to do that. I will going to try to develop one model for one of the different models we had in the lab. So this is GeoStudio 24. Choose best available option. It should be metric 2D, and then double click on Seep W. It will going to take some time. And then we can start drawing the problem that we have. Okay, I will gonna follow the steps in the instruction sheet that we used in the last lab. Okay, so yeah, now close this. The first step you are gonna do is to go to View Units, and for the length change it to centimeter. So now you don't need to do any conversions for the flow rate or something like that. Okay, so it's just in centimeter. Close that and then go to grid. Okay, this is in view. Go to grid and view. Okay, again view, grid, and for the X spacing change that to the value that you want. I would say the best value here would be 0.5 centimeter. And it's very important just to mention this. If the physical model that you used in the lab had a length of 40.7 or a height of 30.8 or something like that, try to just make it to the nearest 0.5 centimeters. For example, if the length of your model was 30.8 centimeter, you can just draw 30.5. You can assume it's 30.5 just for the sake of simplicity. You can basically do it in the same units you have by changing the spacing here to 0.1 centimeter, okay? But I would say it's just for the sake of simplicity, these tiny values will not gonna change a lot. So if the length of the model was 40.7, you can make it 40.5. You can draw 40.5 or something like that, okay? So after changing the grid spacing to 0.5 centimeters, now you can go to sketch axes, and here you can see it's now in centimeter. So for the model I'm going to draw in Seep W today, it has a length of 59 centimeters. Okay, so I will gonna just write down 59. And then for its height, it had a height of 40.5. So I will gonna make this 40.5. And it's very, very important to change the font size to be 0.15, okay? This is very important, so you can see the values. And then click on Zoom Objects. Now, as you can see, everything is great. And if you zoomed in, you can see that in between the 0 and 10, there's 20 different squares. Each one has a side length of 0.5 centimeter, okay? Zoom Objects, now we can start sketching the problem. It is very important to mention that sketching the problem is not required, okay? But it just will gonna help you to visualize the problem, to understand exactly or to see exactly what the model looks like, okay? But it's not important, it's not required. You can just directly draw the regions. But I will gonna sketch, okay? So here you can see that it shows you the length of the line that you are drawing, the coordinates, the X and Y coordinates of the point that you are at, and the angle and all these things. So now I'm at 0, 0, okay? I will gonna move to the right 59 centimeters. That is the width of or the length of my model, okay? And you can see that the length of this line is 59 centimeters. And then I will gonna go up. The length of or the height of my model was 40.5. So you can see that here I'm at 40.5. I will gonna click here and then go to left and stop at 0. Okay, stop at 0 and 40.5. And then go back to the origin at 0 and 0 and close it. Do the same thing, add more lines for the barrier you have. So the barrier I had was at 22.5. So as you can see, and I'm now at 22.5, but I just want to start this at the top of the sketching area. So it's at 40.5. Then it was 26.5 long barrier. Yes, I will gonna stop here, and then it had a width of 3 centimeters, and it was going up for 7 centimeters. And again, I'm just reading the length here, okay? The length is 7, and then it goes to the right 12.5. Again, I'm just reading the length, 12.5. Stop here, and it goes up to for 14.5 centimeters. Stop here, and then close that at the beginning or at the origin, okay? And as you can see, it did not really close to this one, but again, these are sketch lines. It's not a big problem. It's not a big issue. These lines are not really real lines. They're just to help you visualize, okay? So don't worry about that. Now I will gonna try to draw a line for the upstream, the inlet. If you can remember that there was an inlet for the water and outlet, and the inlet was the upstream level and the outlet was the downstream level, and 2 lines for the soil level or for the ground surface level, okay? So again, sketch lines. So my upstream, my inlet water, the water was inletting the system at 38 centimeters from the datum, which is at the bottom of my physical model. So I will gonna start at 38. Yes, it's here, and I will gonna stop here. Okay, and the same thing, I will gonna draw a line for the downstream. It was at 26. So 26. Yep, it should be here. Yes, 26. Okay, and it stops here. Again, you can see that these are not closing and not matching. It's not a big issue. Basically, we just want to have an idea about what the problem looks like. Yeah, I don't want to make this video too long, and for that reason, I'm just doing this very quickly. For the soil level, if you can remember, guys, that the soil was about 4 to 5 centimeters below your downstream water level. So I will gonna assume in this case that the soil height was 22 centimeters from the bottom, from the datum. Okay, so your datum is here, and your downstream is at 26. I will gonna make the soil level to be at 22. But this, you should have all these values from your physical model lab. Okay. Some of you, I can remember, just added the soil exactly at the outlet level. So at that case, you only will gonna have one line at the downstream level. Okay. So this line goes here, and then the same line will gonna be in the other side too. 22. Yes. Oh, the 2 lines are not exactly at the same level. So this is at 22. What about this one? Oh, okay. Yeah. So this line should be redrawn. Yeah. It now looks good. So now, as we can see, this is how the problem looks like. So this is the soil level at downstream, this is the soil level at the upstream, this is the upstream water level, this is the downstream water level, this is the barrier with all its dimensions. Now I can start drawing the region. Okay, so I will gonna go and start drawing the region. But before drawing the region, it's very important to go to View, Preferences, and click on which one? Yeah, click on point labels. We don't want the point labels, okay? And we don't want the points. Or you can just, if you want them to look to be seen, you should change the text size to be to 0.15, okay? So you can change the text size to be 0.15 for all these things. because these will going to be very big when you are going to start drawing your region, and for that reason we are changing them. Okay, so you can change these to 0.15 and click on point labels so you don't see them. Okay, now I can start drawing. I will going to go to draw, okay, then regions, and now I can start drawing. So for drawing, you should be very careful. It's not flexible as sketched lines. Here, you should be very careful about that. Okay, so I will gonna start, yep, at this point, and then it will gonna go to the 0, and then it will gonna go here, go up to the soil level. Okay, and then go here and here. I need to, yes, and yeah, I'm just trying to draw the region. And here I can close it. And when you are closing it, you are going to have a label for this region or a legend for this region, okay? And it will going to turn into, as you can see, it's a solid area. So you can see that, oh, there is something happen. The next step, according to the sheet we have, the instruction sheet, would be to define your materials, okay? So I will going to go to define materials. Define, then go to materials, add a new material. For your new material, choose it to be saturated only. So all the soil was saturated. We are assuming that. And enter your constant head conductivity value. You did a constant head test, as you can remember in the same lab. And you did it for 3 or 5 different times. The average for the conductivity should be added here. I will gonna assume that the conductivity here is 0.009, okay? This is just a value that I made in my mind, but you should add the value that you have from the lab. And you can change the color if you want of this soil. For me, it's okay to be yellow, okay? Then close that, and now assign the materials to the region you draw. Go to Draw, Materials, and click on this region. And as you can see, it turned into yellow. So that means you just applied this material to this closed region. Close that, and then this next step in the instruction sheets is to go to Define, go to Boundary Conditions, add 2 new boundary conditions. So new boundary condition, change the kind to be water total head, okay? And for my upstream, in my case, the upstream, if you can remember this line, where is it? This line. It was at 38. So this, which is the inlet level, where is your inlet from the bottom of the physical model? Okay, where is your inlet from the base or from the bottom of your physical model? Okay, this is different between the different models. Okay, so in the model that I'm developing here, it's 38. I measured that in the lab, and it's 38 centimeters from the inlet water, from the water inlet to the bottom of my model. And I will going to change the color of that to be dark blue. Okay, then click OK, and then add a new material. You can just make it clone and change the name of that to be downstream. I will going to name the first one to be upstream. So for the downstream, you can remember it was at what? It was at 26. So I will just going to change that to 26 centimeters. Okay, and this was the downstream, and I will going to change the color to light blue. Or maybe this color has a different name in English, I'm not really sure, but anyways, okay? I will going to call it light blue. Go again to the first one. I just forgot to name this upstream. So I'm going to change this to upstream. And now I have my upstream at 38 centimeter, my downstream at 26 centimeter. And again, the upstream is the inlet of the water to the system, and the downstream is the outlet of the water from the system, and both from the bottom of my physical model. Okay, you have all these measurements, or you should have all these measurements. Okay, now then close that. I will gonna apply these boundary conditions. Go to draw boundary conditions, choose upstream. Okay, and where is the upstream here? It's here. And then change that, or choose from the list the downstream, and move this and click here. That is your downstream, and you can see again the two colors of both upstream and downstream. What is the next step? So the next step after defining and applying the boundary conditions is to mesh to mesh the draw, or mesh the regions that I draw. So I will gonna go here, and as you can see, draw mesh properties. It will gonna be 100 centimeter. 100 centimeter is very coarse mesh. We can't use that. You should change that to 1 or 0.5 or something like that. For me, I think 1 is okay. So okay, I will gonna make it 1, and that's it, and then close that. What else do I need to do? Just run the model. It's the time to run the model. Okay, so I will gonna go here to the solve manager and start. I will gonna save this to be, for example, test. Okay, to be test. Okay, and I will gonna save it in the desktop. Oh, I have test, so I will gonna change that to be test 2. Save that, and now it started running. It will gonna take some time. That depends on the size of the mesh you choose. The finer the mesh, the more time it usually takes you to solve the problem. 1 centimeter mesh is not a very fine, and it's not coarse basically, so it will gonna take a couple of seconds. I don't love these arrows, so I will gonna click here on that. No, not this one. Where is it? This one. Yes. So now this is the model. I want to show the water total head. I will gonna go to this list and choose water total head, and as you can see, that is my water total head. So these are the equipotential lines. Okay, these are the equipotential lines. I can draw the flow lines by clicking on here, draw flow path, and add 5 or 6 different flow paths. Okay, so this is 1, 2, 3, 4, 5, and 6. These are 6 different flow. I will gonna add 1 here, just to help you see how it makes a curve around this barrier here. Okay, that how the flow lines are making a curvy line around this barrier. So these are the draw lines. What else I should show? You can very simply go to graphs, and then go to add, and you can name this graph. I will gonna make it discharge. Okay, discharge, and choose this to be flow, water flow, then choose water rate, and choose time. Okay, you can play with all these things. I would say it's very important to try to spend a couple of minutes playing with all these different variables and see what they are, what do they really mean in a real world. If this is a real world dam, what all these different things means in reality. But here we just want to see the amount, the discharge, which is the flow of the water in a specific time. Okay, so we're going to choose time, and I want to see the sum of all the flow in y direction, or in both directions basically, versus the x value, which is the distance here. Okay, and then you can go click on set locations. Okay, and draw and change this to be subdomain cross section. And you can draw from top to bottom or bottom to top. The only difference will gonna be the sign, okay, the sign of the value. So if the water is entering the system, this is in negative. If the water are leaving the system, this is in positive. That means if you draw the line from the top to bottom, for example, it might represent the flow of the water from the upstream to the downstream. That means some water is leaving the upstream to the downstream, and it will gonna be positive. Maybe if I draw it from the bottom to the top, it will gonna be the other way. That means some water is entering the downstream from the upstream, therefore it will gonna be negative. So let me try from the bottom to top to bottom. Okay, I will gonna try to make this vertical line, and then click on show graph. These are in negative. Okay, that means the water is entering the system. That means, as you can see, these points are in the right. Okay, while these elements are at the left. That means water is entering the downstream, and it makes sense that it's negative. I will gonna do that again, but from the bottom to the top, to just show you that it's, in this case, it means that the water is leaving the upstream to the downstream, and therefore it should be positive. Okay, show the graph. The points, can you see the point? The points are at the left of the elements. There's like green elements, small green squares, and then we have these dots on them, the blue dots. So the blue dots at the left, that means the water is just leaving the upstream to the downstream. That means the reading will gonna be positive. It's the same value. The only difference is basically the sign, or so it's positive or negative. So as we can see, if you are here at this point, what is the flow rate? What is the water rate? It's 4.9 centimeter cube per second per centimeter. Okay, so per centimeter width. But at the bottom, it's less. Here, it's 3.9 centimeter cube per second per centimeter. Okay, width, per centimeter width. So how can I compare this value to the value I have in the lab? So in the lab, we collected some water from the outlet side in a specific time. Let me assume that you collected 200 cubic centimeter or 200 milliliter of water in 10 seconds. Okay, so if we divided 200 by 10, this will gonna be what? This will gonna be 20 centimeter cube per second. Okay. But this value should be divided by the width of your model, of the physical model. And I believe all the physical model had a width of 7.5 centimeter. So this will going to be 20 divided by 7.5, which is equal to 2.66 centimeter cube per second per centimeter width. These values should be compared to the values you're getting here. Okay? So these values you have here are in centimeter cube per second, and it's per centimeter. It's not showing because it just gives you the values for 1 centimeter depth. Okay, and change the time. The time is in days. We want to change this. Go to default and change it to second, and then click here on auto refresh and do a refresh. Okay, so now the time is in second, and these values are basically centimeter cube per second per centimeter. So yes, that was one thing. What else we need to show? The second thing we want to see is basically the exit gradient. Okay, so I will gonna close that and go now to view result information, and you can go here to this element and choose it, and you can see what is the water gradient, okay, or y gradient. Okay, they are both basically the same thing, or almost the same thing. The water gradient is the average of both x and y gradients. The x gradient is a tiny number here. Therefore, the water y gradient is the dominant one, and it looks very similar to the water gradient. Why? Because the x gradient or the water x gradient is very small. It's a tiny value. So, and why it's in negative? We said that because the direction of the water is up. Okay, water moves up, which is opposite to the direction of the gravity. So for that reason, you can see that it's in minus. Okay, and Seep W divide each element into 4 smaller elements. You are going to have the 4 values for each one of these 4 elements: 1, 2, 3, and then 4. Okay. The highest value is the value that represents this element, the one that is exactly next to the to the top left. Okay, So you can close that. What else I can see? I mean, these are the things that we want you to show, but you can actually play with lots of things. You can see the pressure head. You can see the water head or poor water pressure, okay? And you can go to, for example, to contour labels and add some contours here if you want. Okay, these contours shows you the different values. For example, here we are showing the poor water pressure. You can do the same thing for total water head. So let me click on that, and then you can add these different contours. Okay, and as you can see, the head value is the same on each equipotential line. Okay, and it decreases as we are moving from the upstream to the downstream. You can also show things from here. You can show basically a legend that explains exactly everything. So we can choose here water flow, and then we can see the water gradient, for example, water Y gradient. Okay, so these things can be seen too. You can show lots of things. You can show lots of different things. You can go here again and choose the water flow, or change that to water to yes, water total head, and the water flow. And here you can choose water flux, for example. It's all going to show you how the water basically moves, the pressure, lots of different things. Okay, and you can show the legends too. Perhaps the legends are going to be very big, so we can then change the size of them. Yeah. Okay. So I hope this video all going to help you to understand how to draw the physical model in SeepW and use centimeter instead of meter, and change the grid spacing and all these things. Okay, so yeah, that's everything I have for today.